it's recording. Yes. So, welcome everyone to our session today. My name is Mohammed Jaber. I am a researcher at the University of Miskolc working on the CiRCLETECH project. Today's session guest and speaker is Sándor Nagy. He is an associate professor and the director of the Institute of Raw Materials Preparation and Environmental Technology at the University of Miskolc, Faculty of Earth and Environmental Sciences and Engineering. Sándor Nagy has been a dedicated member of the university since 2003. The same year, he graduated with a degree in process engineering. His research interests are diverse and significant. They include mechanical preparation of waste, electrical and electronic equipment. I think this is the abbreviation for WEEE. And end-of-life vehicles, the development of processing technologies for municipal solid wastes, other wastes, and biomasses, and also the study of agglomeration. So today's session or workshop title is Processing Technologies Input Waste Streams. This session is recorded. We will upload it later to the CiRCLETECH Hub website. And please feel free to write your questions in the comments. And also we will have enough time after the presentation for discussion. So you can also later use the raise hand option in Teams and ask your question. Dr. Nagy, the floor is yours. You can start. Thank you.
Okay, thank you very much. Please give me a feedback if you can see my presentation.
Yes, we can see the presentation and hear you very well.
Okay, thank you for the feedback and welcome everyone who are here and listening this presentation. And thank you for the introduction, Jaber. As Jaber mentioned, processing technologies input waste streams is the title of my presentation. Of course, a lot of people worked in these topics, but will be introduced. And I will, okay, if I can change the first slide, maybe the computer is not so fast.
Technical issues can happen.
At the first slide.
Yes.
Okay, let's see. Okay, now it's maybe
now we are okay.
I just summarize here the content. A short introduction of our institute. I think the topics which we are dealing with are quite interesting for me, at least. And I would like to invite you later a virtual lab visit. And I would like to introduce you waste streams, LCD displays, OLED panels, LEDs, batteries, vehicle electronic and vehicles. And the aim of my presentation is to focus a little bit on that in the vehicles there are a lot of different kind of electric equipment and electronic equipment, such as display panels, electronic sensors and batteries, which were not there maybe 20 years ago or 15 years ago. And so these waste streams are a little bit mixed. Actually, a vehicle and modern vehicle containing a lot of electronic waste, which should be maybe considered that how to process the cars. If we just put the end-of-life vehicles in the shredder plant, then maybe we will lose some important materials or elements. Our institute is 101-year-old Institute of Raw Material Preparation and Environmental Technology, the long name institute. And in our faculty, Earth and Environmental Sciences and Engineering, we have 5 institutes, and we are one of them. Our activity from process-wise, if you look on our institute, then the crushing, grinding, fine grinding, mechanical activation, classification, reactions technique, biotechnology, handling, bioprocessing, let's say bioprocessing, handling of particulate matters, and agglomeration processes. From the material-wise, primary raw materials, tailings, slags, ashes, biomasses, and wastes, secondary raw materials, municipal solid waste, electronic waste, hazardous wastes, also water and wastewater, and soils. Of course, the services, we have a large laboratory. We can make a lot of experiments for companies, grinding, separation, and particle design, a lot of different and interesting topics. And also we made, with cooperation with companies, some development of devices for comminution and also for separation in the last few years also, and earlier time also we have some developments, and of course education are there. We are present in all levels, bachelor, master levels, and also PhD levels. We have education. Okay, our laboratories, I don't want to go to details, just maybe interesting to check the main laboratories: crushing, classification, waste processing, nanoprocessing, bioprocessing, wastewater technology, powder technology, industrial minerals and secondary raw materials. And the newest laboratories, the 10th Laboratory of Innovative Fine Milling and Particle Design Technologies. We have here a lot of high-tech equipment, particle size analysis, scanning electron microscopy, and so on. I will have some pictures also, I hope, from this laboratory. The second part, the virtual lab visit. We are located in a large hall, the first hall of the C2 building, with 3 more institutes. We are the largest one in this hall. And also we have here a lot of machines, equipments for fine milling, separation, the current separation, also fine milling, particle size analysis, and classification, and agglomeration equipment, flotation, powder technology, sample preparation, fine milling, and biotechnology. Show some examples. The newest laboratory, the particle design laboratory, can be seen here, and also particle size analysis, microscopy, and fine milling of particles can be seen here. Some relevant running projects or projects which were closed in this year or last year. The CiRCLETECH, of course, is one of the most important projects in our institute, which in the frame of this project, you can hear this presentation, the Mind Talk project. 3D foam, it's a foam geopolymer made by additive manufacturing for construction technology application. Sustainable raw material management and thematic excellence programs. Different kind of programs are running or were closed in this or last year. We also have a lot of industrial research works. I just put the research work from the last from 2021 and 22 and check the main topics of this research works for industry, direct industrial cooperation. And I have here these words which were important: fine milling, waste processing technologies, RDF, design of separators, fly ash, wastes, wastewater, sludge, lithium-ion batteries, byproducts, municipal solid waste geopolymer, which were the most important things in these years. Grindability, primary raw materials, wastes, pigments production, micro and nano milling, composite materials, mill design, material properties of bulk materials, classification, separation, design and analysis of technologies. Sampling is very important thing. We also made a large sampling for municipal solid wastes for the whole country in 4 seasons. It was a quite large work to analyze the composition of the municipal solid waste stream for whole Hungary, and utilization of residue materials from end-of-life vehicles, VE, lithium-ion batteries, and so on. Oh, it's okay. Sorry about that. It's this slide. It's the wrong one, not the English version. It's about the circular economy, but I think all of you is well familiar with this. I don't have to go to the details. I have seen here some data from the VEEs, electric and electronic equipments in the European Union. It's quite a large amount is put on the market from electrical and electronic equipments, more than 13 million tons, and a large part of it is collected as e-waste, and it means 11 kilograms e-waste is collected per person in the European Union. You can see that there are more possibilities, and because there are a lot of this type of electronic equipment. Just some technological backgrounds about the mechanical way of the preparation, because I'm dealing rather with the mechanical preparation, and so make concentrates from different kind of materials, which later can be processed by hydrometallurgy, pyrometallurgy, or biological treatment methods. If we have some waste stream electronic equipments, the first step should be actually the comminution or disassembly. It means that we should liberate the different kind of materials and parts of it, so we can separate the structural, so-called structural materials, for example, aluminum, cable waste, copper, and iron, and plastics. And after that, we can make the different separation steps. It means according to the differences in particle properties, we can separate different fractions, which fractions are rich in structural materials. And after that, the next step is maybe hydrometallurgy or bioprocessing or pyrometallurgy can be the next steps. The products from the separation may be plastic housing, printed circuit boards, some metal parts, cables, and so on. You will see here some examples during this presentation during today. First, I wanted to show you this bad example. There was an interesting analysis what is happening with the electronic waste. And there are some leakage in this field, and a few % of the electronic waste goes to the wrong way from European Union, and also a larger part from the United States or America. And here is, for example, some illegal deposits from electronic wastes in Africa, in Middle Africa. Of course, it's a very bad situation that it can happen actually, but it's also important to mention that some problems are also in this field. But of course, not all the waste goes to Africa. Fortunately, we have a lot of companies who are dealing with waste processing and doing actually the recycling. Here there was this experiment, and some electric equipment was equipped, end-of-life equipment was equipped with GPS system, GPS parts, and so it was checked that some of them went to Asia and Africa, and from Europe also some waste streams went to Africa and Asia, which actually is not really legal, because this wastage should be processed in the original company, or actually not transported to landfill to other countries. Okay, the critical elements are a very important thing. I have to mention the newest list from last year can be seen in the table, and it's always changing. There are always new elements, and some elements are removed from the list, and we have a lot of projects and industrial cooperation to find and try to recover the critical elements from secondary raw materials and also from primary raw materials. Today, of course, I would like to talk about the secondary raw materials. What are in the secondary raw materials, and how is it possible to maybe make a rich fraction from this material for the processing by mechanical way. I have here collected here some challenges in the recycling of these materials. There are some problems of valuable element, critical elements recovery from the secondary raw materials. Let's see them. Assumes the separated collection. If I haven't here this pen, I have a nice pen, and the end of the pen I have an LED lamp. It's a very good, and I like this pen, but I'm afraid that when it will be end of life pen, then actually the LED will not be processed well, and we have LED lights at home, in the toys of children, and in bicycles, cars, LCD display panels, and it's quite hard thing to collect them and process them together. Separated collection is very important. In some cases, there are very low concentrations of the valuable element. You will see some examples for that. For example, the LCD display panels, there are indium tin oxide layer, and it's a thin layer, very low concentration. And the same situation is, or more bad situation in the LEDs. A lot of interesting elements from the periodic system, but the LEDs mass is very low, and the concentration is also very low from these materials in the LEDs. There are complex structures, thin layers and coatings. For example, in the LED, you will see very thin layers, hard to remove and hard to leach them from these materials. Quantities which are used in the electronic equipment can decrease during the manufacturing technologies development. It means they have more product from the other hand, from the one hand, because these technologies can reach more and more people worldwide, and there are more lower concentration in these equipments. The producers try to decrease the amounts, and so decrease the production cost of the product. It's good because they use less valuable materials, but during the waste processing, it's a little bit hard because there are less value in the product, and maybe it's harder to remove them because of the structure and smaller concentration. Significant plastic content, and plastic content is increasing as we started to deal with LCD display panels. We dismantled a few, maybe 15 or 20 LCD monitors and TVs, and there were quite large amount of iron as a structural material inside the TVs and monitors. And nowadays, in a LCD display panel, there are actually no structural iron, just the whole TVs plastic, made from plastic. Okay, and the changes in the technology or diversity is very important. In the TV, the display panel, you can see, you can remember the PDP, CCFL backlight, LCD CRT TVs, LCD LED, and OLED TVs, and also in the battery former was the nickel metal hydride, and now the lithium-ion batteries, and there are now newest technologies, natrium-ion batteries and lithium sulfur batteries. The changes in the technologies are very large challenge, because we also worked with the company for LCD display panel processing, and we designed the technology for them, and they didn't make this technology because they're afraid that maybe there will be a new technology after the LCD display panel, and the new technology will not fit to the then a new display will not fit to the new technology maybe, and so they cannot process them. Also, the battery also the material substitution, element substitution is an interesting question. For example, a new type of lithium-ion batteries, and this also can be a problem today, that some lithium-ion batteries containing a lot of large content of cobalt, which is very valuable, and the newest battery types, for example, the lithium iron sulfur batteries, it doesn't contain really valuable materials, and so they process the same amount from the valuable one and the same amount from the non-valuable material, and from the non-valuable they cannot sell actually for a large price secondary raw materials, because only iron is there. Okay. And the market price is also a very important thing. It was also one reason for the company. He said, okay, I don't want to make this indium recovery technology, because if maybe I check the price in 2006 for the indium, then I can see it's $1,000 for 1 kilogram. And maybe I make the technology, the processing technology, and after 2 years, I realized that the indium price was decreased less than a half price, and so it will be not economical, the technology. That's why it's also a hard topic, the changes of the prices. Okay, in the case of our first waste stream would be the LCD display panel. I think everyone knows the tendencies on the TV market. There were different kind of equipment, the old one, the CRT TVs, and there were the PDP display panels and the projector TVs and so on. And nowadays, actually, this slide is not the newest one, but the situation is almost the same. There are the LCD display panels with LED backlight, and also the other type of the TVs are the OLED TVs. It's much more expensive than LCD TV, but it's on the market. Okay. The LCD display panel waste will increase during the time. Maybe the lifetime is 5, 6, 8 years of such kind of equipment, and also in the waste streams they are present. It's a quite difficult structure. You remember what I mentioned, that different difficult structures are present in this high-tech equipment. It's a sandwich structure from color filter and TFT glass layers and 2 polarizer films. Maybe this slide, I hope you can see my mouse. Actually there are 2 glass layers, and on the surface of them there are polarizer foils, and between the glass layers there are the liquid crystal molecules. And if we switch on voltage on this liquid crystal system molecules, then they can actually change the direction or the polarization of the light, of the backlight, and so this light can go through this system. If we switch off the voltage, then the light will stop, because of the polarizers are doesn't allow to go through for the light. And in this part of the glasses, in the inner side of the glasses, is the indium tin oxide layer, as you can see here, also ito layer. The first glass is the color filter glass, which can make the colorful picture, and the TFT glass is the bottom glass, which containing the actually the TFT, the thin film layers. Okay. We measured the composition of them and what is inside this material. We realized that indium tin oxide is there. Indium tin oxide is the electrode material. Why? Because it's transparent and conductive and heat resistance. That's why this quite expensive material is used in the LCD display panels. In the former CCFL backlight, we find a lot of rare earth metals. And in the nowadays used LED backlight, gallium and indium and also other interesting elements were found. And of course, in the printed circuit boards, there are also interesting elements. The amount of this indium content is 174, we measured a little bit less, milligram per kilogram in the display panels, not in the TVs, not in the equipment, only in the display panels. It's a quite low amount of from indium. During our experiments, we collected a quite large sample. You can see here we realize what is the producer, what is the type of this equipment, and we realized that the LCD panel itself, it's maybe 7 to 15% by mass of the whole equipment. The mechanical preparation technology was the following. The LCD displays were manually disassembled, and the LCD panel itself was thermal treated to remove the polarizer foils. After that, there was a grinding process, and with ultrasonic and chemical baths, the liquid crystal was removed from the surface, inner surface of the glass. After that, there was a grinding in hammer mill below 10 millimeter, and after that, there was an acidic dissolution, and so the acid was able to remove from the surface of the grinded glass the valuable indium tin oxide layer. And after that, of course, precipitation was made, which generated the valuable materials. You can see here the composition of these TVs. You can see this one, for example, what I mentioned is a quite large piece of iron is there. You can see here in the LCD monitors, the metal content is 35%, and the plastic content is 44%. The other one has here the LED backlight system. These dots are actually the LED backlights, and you can see the electronic here, the printed circuit boards for the power supply, and the printed circuit boards for the picture generation. Here's some optical microscopic pictures about the CF glass, the color filter glass, and from the TFT glass is mentioned here. And actually, the indium tin oxide layer cannot be seen on these pictures because it's optical microscopy, and this layer is actually transparent. But here on the scanning electron microscopy, this gray color material is actually the surface layer, which is made from indium tin oxide and responsible for the voltage and the transparency. Okay, here you can see the measured indium values. Okay, here the composition according to our measurement, what was found in the TFT glass and CF glass. The average specific indium content was 131 milligram indium in 1 kilogram of LCD panels. It means only 16 milligram in 1 kilogram of flat screen equipment. It's a quite small amount. The company which was cooperating, it said that, okay, it's actually could be an economic technology if we focusing on the wall processing of the TV panels. If we can remove the iron cables and so on, after that it could have sense to remove the indium content also. The indium price we already discussed about it. Other type of the equipment, I don't want to go to details, but in the ESCC conference we have a paper. We will have a paper about that. The OLED display panels, it's a different working principle as the LCD display panels. You can see here actually organic layers which can light up if we switch on voltage on these layers. Also there is a layer which needs the indium tin oxide layer, but actually there is no backlight necessary in this case because the organic layer itself will generate the light. You can see here the electronic parts of the display panel and the organic materials on optical microscopy. The different color organic materials can light up as subpixels, 1, 2, and 3 subpixels, and together the 3 subpixels are generating 1 pixel. Okay, our next topic will be the LED, light emitting diode, the structure of it. It's a good example for a very small piece is actually this LED, and very thin layer on each other. And the gallium nitride, indium nitride is very hard to remove these layers. And but there we also can see some gold wires. You will see here later on the optical microscopy. And as you can see, the thickness of this layer is approximately 4 micrometer, and the LED chip, what you can see here, is 100 micrometers. So it's really thin layers can be seen here. There are everywhere at home, the workplace, and in the backlight system of the LCD display panels. You can see here that one, and here a small piece of LED, and here is also on this board a lot of LEDs. We checked the literature, and a lot of interesting materials were in the LED backlights, for example. We also checked the plasma screens, but it's not really so important because the technology doesn't exist more, only in the waste streams. You can see here the different materials, and also we measured actually more different rare earth elements in the LED, LCD backlights in the LEDs. Some optical microscope pictures can be seen here. Maybe we can focus on this one. This is the wall LED, almost the wall LED that you can see here. And the LED chip itself is this sapphire structure, what I mentioned you 2 slides before. And the gold wires can be seen here. These are pure gold wires. The problem is that amount is very small. One piece of LED has a very small mass and size. And here you can see the pure gold wires and the LED chip itself. And we made a little bit removed this layer, and you can see here the sapphire structure. And actually here, maybe you can see here the different layers. Maybe some slightly difference in the colors can be seen on this picture. Some scanning electron microscopy. You can see the LED chip here. It's a sapphire structure, and this 4 micrometer layer on it, which containing the interesting and valuable materials. And here the iron wire can be seen. During the experiments, we realized that approximately 50 or 70 LEDs are in one TV or one monitor. The mass of one LED is 0.02 gram. Amount of gold is very low amount in one LED. So the problem is that very small amounts, small masses and so it's very hard to recover them, and we can afraid that actually these valuable materials are actually dispersed in our Earth when it's in LED, because the processing of it's quite hard. Okay, we developed actually an experiment. We made an experiment, and with a few LEDs, we tried to remove the LED chip from the LED itself. And first of all, we removed the LEDs from the panel. It was made easily. If we heat it up, then it was actually easy to remove. Mechanical preparation with grinding. We started with grinding to liberate actually the different parts of the LED. After that, we made a separation by conductivity. It means by electrostatic equipment, we were able to remove the copper part. It's a quite large amount, the copper part of these LEDs. It's important to insert the voltage or electricity into the LED. And the separation by density, we were able to separate the LED chip from the plastic parts. The LED chip, the sapphire, has a larger density than the plastic, and so it was falling at the bottom of the liquid, of the heavy liquid. And after that, you can see here the LED chips separated from the other parts, the copper parts and plastic parts. After that, we made the separation by density, and after that, an acidic dissolution was made, but it's very hard to open this gallium nitride, indium nitride form, so it's a quite large challenge how to remove them from the sapphire structure. This is actually a chemical analysis from the LED, from the ball LED backlight, and from the after the mechanical preparation, what we received product, the LED backlight chip. You can see here that the gold concentration was increased from 170 milligram per kilogram to 30,000 milligram per kilogram. And of course, because this gold was going with the LED chip, fortunately, the gallium concentration was also increased by 2 magnitudes, actually, just that we removed the sapphire LED chip with mechanical way, and also the indium was increased, and the copper content was actually removed because it was sent to another product, a clean copper product. So with mechanical preparation, actually the valuable material content was possible to increase with 2 magnitudes. Other topic, the batteries, the lithium-ion batteries. Also can see here some Hungarian language. Different sizes are present, from mobile phone to power tools and electric cars, and also electric locomotives. This is maybe the largest one, or for stationary energy storage system. They are quite large, and also it can be a problem if we have some electronic equipment which containing built-in lithium-ion batteries, and actually when we throw away this equipment, then it's very hard to remove from that or handle the small piece of lithium-ion battery. We started the experiments at that time with mobile phone batteries. You can see the structure here, and here we dismantled some mobile phones, the different foils, anode cathode foils, and anode cathode active layer can be seen here. We also work here with a quite large amount of sample. We analyzed all of them, made photos from that, and all data which was available we put in this table. After the mechanical processing, actually after a grinding, removal of hazardous materials, and actually the separation of the black mass, the valuable fine materials and the separation of the larger fractions, the aluminum foil, copper foil, and plastic foil separated from each other. We made here some analysis about the batteries. The housing was 20%, covering 5%, anode cathode material 75%. You can see here different producers, but the values are almost the same. The structure is almost the same. And here's some chemical analysis from the smallest fraction, from 0 to 500 micrometer. The cobalt concentration was almost 25% in these parts, and the copper and aluminum content was quite good removed. 0.9, 0.3, and 1.1% was made, and lithium amount was 4.6% in this battery. You can see here some scanning electron microscopy. In the black mass, actually, you can see the carbon, actually the graphite particles, and the valuable metal mixture particles. You can see here one particle are black and other one is actually gray. And we make here the analysis, and you can see here the cobalt concentration. It's quite large in the mass in the metal mixture, and of course the black particles are large particles. Laptop, notebook batteries were also investigated, and I put here this picture about a mild hybrid car battery. It was quite hard to open it and handle this battery. It was absolutely not recycling friendly designed. It's welded together this stainless steel housing. It's impossible to open, only with force, and also inside the cells were made so that it's very hard to work with this type of battery. Other batteries which originated from end-of-life vehicles, for example, this one, if I remember, is a BMW i3, and this one is from a Ford Transit mild hybrid car. This is the covering of it. This is a complex system with battery and with inverter and electronic. It's in a plastic house, and these battery cells are here inside this packaging, and we also made the mechanical preparation for that. It's a very hard topic to remove, of course, the hazardous electrolyte and any other materials, and after that make the mechanical preparation. You can see here, I don't know from which one, maybe from this one, the generated black mass can be seen here. Here you can see the inverter of this box, and actually the batteries can be seen here. We made an analysis for this packaging, or for this equipment, and the system case, inverter, cooling system, and other parts were there, and the analysis can be seen here. Actually, what is the composition, plastic or printed circuit boards, and any other structural materials can be seen here, analyzed. Okay, I would like to go to actually the last topic, when we are focusing on the vehicles and their parts. And I would like to mention here that in the vehicles are actually almost all the electronic equipments present in the new vehicles, but which were introduced here. Also, LCD panel, LEDs, lights, front light, back light inside the car, lithium-ion batteries are present in these vehicles. Vehicles per capita in the European Union, there are almost 600 vehicles per 1,000 inhabitants. It's a quite large amount. In Hungary, we have approximately 400 vehicles for 1,000 people, inhabitants. It's from a former one. I don't know why the newest one was inserted here, but the situation is the same, a little bit increase in both cases. Okay, there are some so-called new parts, we could call so new parts in the vehicles, what I already mentioned, a lot of electronic parts. sensors, computers, printed circuit boards, LCD display panels with LED backlights, LED lights. A lot of cars are equipped only with LED lights nowadays, and of course lithium-ion batteries. Maybe in an electric car a large amount, or in a mild hybrid car a smaller piece of lithium-ion batteries. The end-of-life vehicles were processed with standard shredder technologies. Technology, of course, doesn't focus on the recovery of the valuable materials in the new parts. And standard shredder can be seen here. It's a well-working technology. The car goes here, and the shredder making the grinding process, and the comminution process decreasing the particle size below 100 or 60 millimeter, and so the main structural materials can be separated from each other: iron, aluminum, copper, and any other materials. But if a new car is full with electronic, then it's a questionnaire: what is happening with the electronic parts? What is happening with the LEDs and the printed circuit boards and the connection points, which are the pins are covered with gold layer? So maybe they goes to one type of byproducts, or will be removed by air during the grinding process, and maybe catched in the cyclone powder or in the slag in the washing equipment somewhere that they could belong. Question is how to process them. Maybe remove before the shredding this part. Okay, the lithium in battery should be removed. It's absolutely clear. It cannot be fed into the shredder. Should be separated and should be process separated. But what is happening with those other parts which were mentioned here? And also, when a vehicle has an accident, a smaller accident, then maybe the headlight or the whole car will be destroyed, and so also generated this electronic waste type equipment, which should be processed properly. The reuse of them, it could be a good solution if there is an end-of-life vehicle or there is an accident with the car, but then is a qualification necessary if this equipment is still working properly and can be fit into another car. Sometimes it is not possible because the producer said that, okay, this was fit for this exactly car, and it's not possible to fit into another similar car. Here, interesting picture about innovative features which work behind the car safety. These are the electronic parts which are responsible for the safety of the car, not all the electronic parts. You can see here sensors, electronic printed circuit boards, and any other electric parts in the cars. We also dealt with these materials. We have a partner, Automendikar Ltd, and we received some samples from them. This is an ACC, Adaptive Cruise Control instrument. This is at the front of the car and measuring the distance from the car between the two cars. And if the distance is too small, then maybe it can brake or give a warning signal for the driver that, hello, you are too close to the former car. We dismantled it, and of course printed circuit boards were there, and on the printed circuit boards we realized that there are a lot of sockets and pins and connectors, and on the surface of this there are gold covering layer. Interesting, it would be better rather process these parts as an electronic equipment, not as an end-of-life vehicle. Okay, the concentration was not so high, but there were some gold content. Car front LED light. We also had last year, we closed this experiment. A few front full LED lights were procured and analyzed. Composition structure was made, and it's a totally actually a totally complex system with ventilation, with printed circuit boards, with cables, LEDs, and a lot of interesting material. This is the LED itself in an optical microscopy. And we designed for that also mechanical processing technology. You can see here the analysis, optical parts, glass, cooling systems, screws, printed circuit boards, plastic parts, aluminum cooling parts, plastic connectors, cables, and front covering. This is the polycarbonate material. And you can see here the dismantled one. And here you can see a printed circuit boards, and the printed circuit boards, there are surface mounted LEDs on the surface. These are responsible for the light which is coming from this car. And we made an analysis. The mass of one LED is in milligram. You can see it here, and you can see all the number of the LEDs from the printed circuit boards, and the different kind of lights are summarized here. Then the sum mass of the LEDs inside one front light is almost 0.4 gram. Actually, it's a very small amount in one piece of front light. There is almost 0.4 gram LED, so it's quite hard to deal with this. We have here some pictures with optical microscopy. It's a cross section from an LED. We made it a few years ago. This is originated from the LCD display panel backlight, and this one is a scanning electron microscopy picture from a car, from a vehicle front light, what you can see here. And this is the Zephyr system, the LED chip itself. So this is generating the light actually. We also dealt with end-of-life commercial vehicles during a project which was closed in 3 years ago, because the dismantling is not really well regulated in the European Union of these buses or commercial vehicles, and the ratio of the electronic parts is increasing in these buses. And the composite fractions are also important, which technology should be developed for that. In Szolnok, there is a new plant which is able to properly dismantle these large buses or commercial vehicles. And we made also a material analysis, how many percent, what is the composition of these old buses, and what kind of composite materials are inside that. We also we didn't stop in the bus size. We checked the locomotives, and we made dismantling from 2 locomotives. Actually, they just cut the chassis, remove it, and after that remove the electronic parts, transformator, engine, and any other things here, cables and so on. And after that, they just cut this main frame, removing them, and so it can be processed and renewed. What we made here analysis, there were 2 locomotives which were dismantled. The first one is a diesel engine, and the other one is an electric locomotive. This type of the locomotives is still in use, both of them in Hungary. Of course, in better conditions, hopefully, like in this picture. And the diesel engine, the diesel locomotive, were containing 97% iron and 1% aluminum and 0.5% copper. The value of it was actually $14,000 in 2019. And if we made the same composition but larger prices for 2022, then more than double price was realized for the same locomotives. These prices are showing only the prices of the material which is in the locomotive, not containing the transportation cost, dismantling cost, and any other cost, just the value what is inside the locomotive. In the case of the other locomotive, the electric locomotive, 94% was iron, aluminum percent was 0.8%, and the copper concentration was larger than 4%. So the value of it was $40,000 5 years ago, and 2 years ago it was more than $90,000 US. So the prices of the metals also increasing during the COVID COVID period. And the newest locomotives, they can be work with hydrogen and also with batteries. The batteries are also inside the locomotives. These locomotives were procured for Hungary. I think 4 pieces are from that, which containing lithium-ion type battery, but we didn't find any exactly examination what kind of batteries are inside these locomotives, but also in the locomotives the batteries are present nowadays. And I would like to show you this CiRCLETECH project, which was made formal in our university. And in the CiRCLETECH project, there are 10 monographies, and the 10th one is available on this homepage. It's in English language, and it's dealing also from the results of this project. And now I would like to thank you for your attention. I hope that you find this presentation maybe interesting, and if you have any question, then I'm here, and please don't hesitate to ask and discuss about this interesting, hopefully interesting topic. Thank you, Arda.
Thank you very much for this interesting presentation indeed. A lot of information, important information about materials inflows and recycling. We open the floor for questions. Hopefully, if anyone has any questions or any remarks for discussion. I see no question somehow. So maybe it came to my mind because I'm more into economics. What is the economic value? Like, I mean, how it can be economic feasible for these processes for those technologies to retrieve those critical raw materials.
Okay. Actually, as I mentioned a little bit about this, in the case of the LCD display panels, we cooperated with the company, and we designed the technology for the company, and the company said that, okay, it would be economical, but they don't trust it so much to recover these parts, because prices can change, and maybe the substitution can be a problem. But at that point, it could be economical, they said. But okay, it's economical, but not so many profit is on it. And so I think that if we can remove or recover other parts, structural materials, then maybe there is a place for the recovered valuable materials, also the critical raw materials. And of course, if there are so systems that if the company should collect this material and they receive some support for the processing of it, then it can be possible to make it and recover it. In the case of the LEDs, I don't know if it is possible to collect them separated and make an LED processing plant, and so collect from the LEDs from the pens and from the display panels and from the cars. It's a quite hard problem. And in the case of the lithium-ion batteries, as you can see, I showed you that a lot of cobalt content were in the batteries from the mobile phones, but in the end-of-life vehicles, that the newest battery, which is quite safe, the lithium iron phosphate batteries, containing not really much valuable materials. That's why, but the company should process it. Maybe they should receive more funding for that or sources for the processing of that. And what I would like to mention that the problem is, I think that there are new technologies, new equipment, and maybe the processing technologies should be designed maybe before to put it in the market, or maybe some directives should be given. Not that, okay, there are new product, let's start. How is it possible to process it? Maybe it should be designed according to the recycling technologies a little bit, that it should be easier to recycle.
I see. Thank you for the answer. Actually, we have a question from hopefully I will read your name in the right way. Hidayanto is asking
Okay.
about the plastic waste streams processing actual issues, because he's dealing with plastics as a pollutant.
Okay, I checked the question. The plastic waste stream is quite research deal with plastics as pollutant. Okay, the plastic waste is a quite interesting story. After the processing of end-of-life vehicles and electronic wastes, there is a large amount of mixed plastic, grinded mixed plastic. And so it's a very hard task to separate them from each other, because there are different kinds of plastics, and also the additives, the filling materials, for example, glass fiber, any other materials, limestone, making the properties of this plastic quite hard, because if there are some differences in the density of the plastic, we could separate it in the sink float process, put it in the heavy, put it in water. Some of the plastic would swim on it, some of them would go down. But if there are some filling materials, then it's quite hard, because depending from the filling materials. Of course, there are technologies, NER and any other technologies, X-ray technologies, which can separate these plastics from each other. And also in Austria is a technology, as far as I know, which can separate these mixed plastic parts. And the companies who are in Hungary and processing, for example, end-of-life vehicles, plastics, they have more options to maybe landfill this plastic, or send it to thermal utilization, or send it to material utilization, actually, for this separation process. Also, it's a quite hard question, and I'm not really realized what is your research as plastic as a pollutant, in which area is as a pollutant. You mean in wastewater treatment, maybe, or water treatment, or in metal recycling? If you can answer it, then maybe we can discuss about that more detailed.
Thank you very much for the detailed answer for the question. Yeah, plastics, biodegradation.
Biodegradation. Mm-hmm. Okay, it means that you deal with new type of plastic, I think, but in the case of this mixture, it could be also a nice challenge to process it with biodegradation, because absolutely ABS, polycarbonate, and any other different mixture from these materials, and so it's a hard story. Fortunately, in the case of the metals, there are some directives that, for example, the aluminum alloys, there are silicon containing aluminiums and magnesium containing aluminiums, and so it's easily to recycle them from each other. It's also possible to separate them from each other, and so you have actually a good basic material, raw material for the new production. But in the case of the plastic, these filling materials and additives can make these things very hard and challenging.
Thank you again. I don't know, do we have any questions?
Maybe Orshoya, I saw the hand of her for a few seconds, or it was just. Okay, thank you for your question.
Yeah, maybe another question from my side about how do you foresee the future of processing technologies and the critical raw material retrieving from waste under the current situation and the future situation in general?
Okay, it's as you can see from my presentation, it's getting more difficult to separate them from each other. And I think maybe the automatic sorting system can help in this situation also. This is the newest technology, NER and any other technologies. And I hope that maybe the lifetime of this equipment could be a little bit exceed, not maybe just 1 year or 2 years in some equipments. And maybe some regulation could be made that last time for 2 weeks I bought some solar lamps for home, and I realized that in one of them you cannot change the battery, in the other one it's possible to change. Why not can you change the battery in all of them? Because then you could exceed the lifetime of it. Such kind of regulation and the design for recycling should be increased, and so maybe we could handle these issues better.
Thank you very much for the answer. I'm not sure if we have any other questions or ideas. I think by this we can conclude our session today. I would like to thank you, Sándor, for this informative presentation and this discussion, and also extend my appreciation for the attendees for being here today and participate with us, and for the questions. As I said, this session is recorded. We will upload it later to the CiRCLEHub.eu website. I will just write it. You can also take a look at it, take an idea about our work, research groups, and podcast videos as well. By this, I would like to thank you again, everyone, and see you in our next workshop meetup. Thank you very much.
Thank you for coming and thank you for the question.
Have a nice day.
Goodbye. You too.
Have a nice day.
Thank you. Bye-bye.
Goodbye.
Bye.